Welcome, everybody, to our third edition of our online computer vision and artificial intelligence workshop. For those of you who have come to the first and second editions, you guys know that my name is Jose, and I'm a PhD student here at the Nordling Lab in NCKU, and I'm also your lead hacker. So here today with me, we have the same people as usual. We have my assistant hackers, Rain, Jacob, and Rick. Guys, would you guys like to say hi to the audience?
Okay. Hello everyone, my name is Rick and I'm a season hacker of this hackathon, and I'm also a master student of the Nordling Lab.
Hello, I'm Jacob, and also is the assistant hacker in this hackathon, and I also is the master student in the Nordling Lab.
Hello everyone, my name is Ren Wu. I'm the chat master of the hackathon session. Please feel free to write your questions and comment in YouTube and Twitch chat. I will gather them and report to hacker as soon as I see it.
Yes, so thank you guys. I would like to thank all of you for your support, whether you are watching us live or you're watching us later. We really want to say that we appreciate all of you, and if you like our content, please give us a like and subscribe to this channel because we have 2 more workshops coming in the next following weeks. So today, actually, we have a very special workshop for you guys because today we're actually going to dip into a little bit technical stuff because we're going to dig into what is deep learning. So far, we have dig into what is data collection using the OpD. Now we're going to do data analysis, right, using TensorFlow and deep neural networks. So let me show you the outline that I have for you for today. So as I mentioned last time on workshop number 2, which was 2 weeks ago, I hope that you guys had a chance to take a look at that. On that workshop, what we did was we did half of our submission for the OpenCV and AI competition for this year, which was to collect data from Parkinson's disease patients. Well, more specifically, we collected the finger tapping trajectories. So if you remember, we had the subject do this kind of motion, and the subject had like red and blue stickers, and we want to basically extract the trajectories of the fingers. So I want to extract the Euclidean distance of the fingers to assess the motor function of Parkinson's disease patients, right? To assess like, okay, is their motor function good? Is their motor function getting worse, right? And there, well, if you're interested in that, you're welcome to check our second workshop. Now, for this part, what we're going to do is that we're going to use deep learning, more specifically at 3D convolutional neural network, which is a type of deep neural network, to predict these trajectories based on video data. So based on the recordings of the patient. So before we get into the little details of how to do it and why does it work and what is the magic behind all of this, I would like to explain, because we have no idea what level of expertise do you have regarding deep neural networks. So we're gonna start from like the bottom, right? We're gonna start like starting explaining from very basic concepts, and then we're gonna get, so that's the first part. That's the introduction to deep learning. Then we're gonna get into the methods, right? So we're gonna explain what did we do, how did we pre-process the data, right? How do we prepare the data to be served as input for the CNN? And then we're gonna get some explain some results. So we're gonna show the results that we did for the submission, and we also have something special for you guys because we have actually expanded a little bit on those results, and we find some interesting stuff. And then we also can, then we will move into the conclusions, like, okay, what is the whole point of doing all of these experiments, right? And what value do we think that we bring to the scientific community and the computer vision community, more specifically. So the first part is introduction to deep learning. So let's start. So basically, there's many different definitions of deep learning. If you Google right? Deep learning, you will find tons of definitions, and none of them are, I would say, wrong, but also none of them are entirely correct, and none of them fully grasp the concept that we in our lab believe that deep learning is. So if we were going to put it into one sentence, we would say that deep learning is the subfield of machine learning that uses artificial neural networks of multiple layers, because multiple layers means that it is deep, right? If you only had one layer, it wouldn't be deep, so it would be maybe shallow learning. Then we want to use these artificial neural networks to learn higher level features that make prediction a trivial task. So what does this mean? So we want to transform, right, the data through these layers of the artificial neural network, and we want to transform it into a manifold representation in which the task, whether it is regression, whether it is detection, whether it is classification, segmentation, that task becomes trivial, it becomes easy, right? Because you have put it into a space that allows the task to be easy. Here we have this nice diagram. It's supposed to be something that resembles like a Venn diagram of the different hot topics, like these keywords are like hot keywords that you could find. People, most of the times they hear these words and they assume that they are the same thing. Here we try to make a differentiation between all of them. So here we have concepts like, for example, the data science, right? So data science is anything that deals with data, right? And data mining is anything that aims to extract knowledge from data, not necessarily. So here you can see the data mining is part of data science, and some machine learning methods are part of data mining, but not all of them. So let's talk about, for example, what is machine learning and how does it relate to data science. So machine learning is a subfield of it's like a part of data science that uses statistical models, right, that learn the data, that learn from the data itself. So the parameters of those models are updated based on the data itself. Now, deep learning is a subfield of machine learning, as I mentioned in the in the definition. Now, the differences of machine learning and deep learning is that deep learning is it uses multiple layers, right, in order for it to be able to transform the data. Machine learning doesn't necessarily do that. For example, a linear model is a machine learning model, but it's not a deep learning model. A support vector machine is a machine learning model, but it's not a deep learning model. Now, both machine learning and deep learning, they are part of the bigger field, which is artificial intelligence, which is artificial intelligence. Artificial intelligence is anything that resembles human intelligence, right? Anything that seems to be smart. That would be, for example, expert systems. Let's take, for example, that I create a system that can account for many different situations, right? Now that system is not really smart because it's not learning from the data itself. I'm hard coding all of the things in that system, but it looks so smart because I just have taken into account a lot of different scenarios and situations, right? Now, all of these terms, they are part of statistics. Well, at least data mining, machine learning, and deep learning are part of statistics, and some artificial intelligence, because they also contain machine learning and deep learning. And for us, oh, there's something with a microphone. Something turned on the microphone.
So there's a question.
Yes.
The question is deep learning or machine learning more accurate?
Good question. Who asked that question?
Well, if I pronounce wrong, correctly, it should be the rank. Sorry, I don't know how to pronounce it correctly.
Okay. Anyways, thank you for your question. Deep learning over the past, I would say, well, at least since I started my PhD, which was 5 years ago, it has proven to outperform most of the machine learning methods for most of the tasks. But especially for computer vision tasks, deep learning has proven to even outperform humans. And the reason why deep learning is so good, right, is because, as I mentioned before, is able to do representation learning, which is something that machine learning cannot do, right? For example, let's say a linear model, right, would take the features as they are, right? But those features do not necessarily not necessarily create a space in which, for example, let's say if you want to do a classification task where you can draw the boundary decision very clearly, right? However, if you use for example, like a deep learning model, like let's say a deep artificial neural network, like a multi-layer perceptron, that model will be able to represent those original input features into another space in which is typically easier, right, to do that classification. In this case, if you're talking about classification or any task. Now, this obviously comes with a drawback, because that means that deep learning is able to learn representations at a cost of more parameters. But more parameters also mean more data, right? And more data means that you need to find ways to store that data. You need to manage that data, which is not the case for machine learning, right? Machine learning, you can you need relatively few amounts of data to have a model that works well, but deep learning requires much more, right? But you also have the counterpart that the models can work extremely well. Thank you for your question. So then the last term that I want to explain here, if I can have my pointer. Where is it? Let me just make my pointer. So the last term here is system identification, because we are in the mechanical engineering department here at NCKU, and most of the people tell us, like, okay, but you guys are mechanical engineers, right? So how can you guys study deep learning? And then I always tell them this thing, that there's a subfield, right, in mechanical engineering that is called control theory, right? So control theory aims to, being able to, you have an output, how can you get your how you have an input, how you get your output to be whatever you want, right? And typically that happens through a plant. To the input goes through a process to a plant, and then it goes to an output, and then there's many ways that you can control the parameters of that plant. But sometimes you don't know what is that plant, right? You don't know what is that relationship between the input and the output. And then there's a subfield in control theory that is called system identification. And system identification, well, it does that. It aims to find that relationship, right? And that's what we actually do, because in deep learning, we typically also we start with a model that is very bad, and then it ends up being very good through, iteratively changing the parameters and correcting itself to get to a let's say optimal solution, right? Which is in practice is a minima, is a local minima. So yeah, and then all of this part is part of statistics. So let me get into the next slide. Okay, so I touched a little bit about, I touched this a little bit in the previous part. But here, one thing that we need to understand is what is a statistical model? So a statistical model, or a mathematical model, is a set of mathematical equations that describe the relationship between an input and an output. For example, you have let's say you have this plot here. You have x, right? And then you have y. So you have the x being in the abscissa and y in the ordinate. So let's say, for example, that your independent variable, so whatever's in the x-axis, is height. Let's say height, and then you have the weight in the y-axis. So then you could define the relationship in the form of y equals m, which is the slope, right? X plus b, right? So you have defined this equation that helps you to understand how does the weight relate to a person's height, and there is a relationship, right? And typically you would typically your data looks like this, right? It looks like not everything falls in the line, but the trick is to find the equation that can draw this line, right, by fitting the data the best. So a mathematical model will get an input, right? And here we have our model, and then it will be able to transform our input into our output. Now, another thing that is very interesting is that the parameters of the model, so in this case, the slope and the bias, or as we would like to call it, the weight and the bias, right, are defined by, are learned by the model through the data itself. So we don't go there and type, oh, M is this, B is this. We allow the model to learn those from the data itself, which is why it's called machine learning, because the machine is learning those parameters by itself. So in this case, since we are touching a lot of points that are probably outside of the traditional computer vision field, you guys are welcome to at any point go there and type a question, and we will be more than happy to answer. So for the next part, here we have the typical architecture of a deep neural network. I think my assistant Rick has a very good explanation for this one. Rick, would you like to tell the audience?
Okay. So here's the basic structure of a neural network. So for this, we have three types of the layers. One is the input layer, hidden layers, and output layer. So clearly the input layer is for the input, the output layer is for output, and anything rather than input and output layer is called hidden layer, and it's in the middle. So the network, you can see this slide. So the network actually will transfer the feature to the next node of the next layer. So in here you can see the W11 translink to the, that is a Z to the 2 to the A to the 2. So, and I think one big point of the neural network is they usually use the activation functions. And so the activation function is the equation you see inside this node. So it's actually a nonlinear equation. So if we don't use these activation functions, the whole network will actually like just like a linear combination, like matrix ties to matrix. And so with this activation function, the whole network will more good with the nonlinear data. So this is one, I think this is one big point why the deep neural network will perform more good than the machine learning. Yeah, this is my explanation.
All right, thank you, Rick. So just let me highlight some of the stuff that you said, because I think that you actually said a very important point. Okay, so the first thing that you said is that each node here is a linear combination of all the previous nodes. So in here, each node represents like a feature, right? So you can see that, for example, this one is a weighted sum of this node, and the weight is defined by W11 and W12, and then you sum of this, that's gonna give you Z, right? Then how do you get A? Is that you pass Z through a nonlinear activation function. In this case, we have shown the rectified linear unit, you see that it's nonlinear because it's not a line, right? And then that's how you're gonna create another feature, right? And that's how the network does representation learning. It's able to project the features into a different space through this nonlinearity. That's the first thing that you do. So then in this case we have a dense layer, so it will have a combination of all the previous one. You could have a convolutional layer or different types of layer, but in this case this is the most basic one. And then you can see also, for example, for this one, this is a weighted sum of this one, right, through here. Then also this one through this weight, and then also this one through this weight. Okay. Another point that you mentioned that is crucial is that why do we have nonlinear functions in between the network? That's because if we didn't have nonlinear function and we had linear functions, then our whole system could be represented, as a it wouldn't be any, it wouldn't make any sense, right? Because like you said, it would just be two linear operations can be summarized into a single one, right? For example, like you say, it would just be like multiplying, instead of multiplying by two matrices, like if you do linear algebra, right? It would just be, it could just be by a different matrix, right? And then that wouldn't make any sense, and then we wouldn't be able to learn the complex functions that we need the data that most of the problems have, right? Now let's get in. And so for this one, another thing that I would like to notice is that we have the input, hidden, and output layers. So the input layer will take the input features, and then the hidden layers will transform these features into another space, and then the output layer will take these features, right? And then just we apply this activation function that is called sigmoid to just bound our values between 0 and 1, because that's, in this case, is probably what we needed, right? There are different activation functions, right, for different cases. But typically, at least for our case right now, we use sigmoid because we want our values to be between 0 and 1. So, okay. So what is a typical pipeline for designing a deep learning model? So let's say somebody gives me a data set, right? And they say to me, okay, Jose, I give you this data set, which is composed of, in this case, is images of numbers and also their labels. So for example, this picture of a 2 has the respective label of a 2, right? If a 5 will have the label of a 5, right? And then somebody tells me, okay, I give you this data set. I want you to create a deep learning model to classify these figures for me. Okay, so then the first thing that I would think is, the first thing is, okay, what kind of learning strategy or learning type do I want to use? There is unsupervised learning, which is that I don't give the model learns relationships of the data by itself. Like for example, here it can do hierarchical clustering of data by itself. There is supervised learning, which so in unsupervised learning, you don't give the labels to the model. The model just gets the, for example, the samples, like it would just take the images, and then it would try to see, okay, these images look similar, so they must be from a group. These other images are similar, so they must be from another group, right? Supervised learning, which is I give the image to the machine, and I say, okay, try to guess what this is, and then the machine will give me an answer. Say, no, actually, it's this answer, right? And then now we apply a correction to the machine. Reinforcement learning, in which I basically simulate that my system is an agent in a world, in an environment, and then I just give it a reward function, and then it would just try to maximize the reward function by itself. Or transfer learning. But in most of the situations, what we will use is supervised learning, because it seems to be the most effective method for learning. So we're gonna choose that one. We will choose supervised learning. Then the next one is to what kind of model structure there is or design of the artificial neural network, because there are so many designs. There's, for example, a long short-term memory. There is recurrent neural networks. There is convolutional neural networks. There is generative adversarial networks. There is deep Q networks. So this one, you typically realize very quickly that, for example, LSTMs, or which is short for short-term memory networks, and recurrent neural networks, they are used for analyzing sequential data. So let's say what language, right? Language is a sequence, or let's say predicting tomorrow's weather, or predicting the stock market, or doing a forecast of COVID-19 patients or incidents. GANs typically aim to create new data, right? So let's say that you have, for example, you really like the style of painting of Michelangelo, and then you feed the network a lot of pictures of Michelangelo, and then you give it a new picture, right? And then you will try to redraw that picture in the Michelangelo style, or deep Q learning, which is used for reinforcement learning. In this case, deep convolutional neural networks, or CNNs, are the staple for most of the computer vision problems. So we're going to use that one. So then I have my learning type, I have my network. Okay, so now how is this network going to learn stuff? How is this network going to be good? Well, as I told you before, I'm going to get my input, right? And then I'm going to pass it through the convolutional neural network. Okay, here I would like you to notice that there are basically two parts to this convolutional neural network. The first part is the feature extracting part. So in here we will apply convolutions, the convolution operation, which we will discuss in detail a little bit later. This is also a key part of why this network is so good to analyze images and videos in this case. And then we're going to extract the features using the convolutional layers. And then once we have features transform into another space, hopefully that space is better, then we're going to use a predicting layer, which is most of the times is a fully connected layer. And then we're going to get an output, right? Now, the output is going to be compared with the ground truth, right, through a loss function. The loss function is going to tell me, or not me, it's going to tell my model, oh, you are very off. Your prediction is super off. You need to you need to do better, right? Or your prediction is super good. Now, once I get that loss value, so now this is a very interesting part about deep neural network. So we have backpropagation. So what is backpropagation? Backpropagation basically refers to doing a backward pass of the model. So here we do a forward pass because we put the input, and then we're pushing the input forward to the neural network to get an output. Now I'm going to do a backward pass. So I'm going to get the output and I'm going to pass it back through the network. Why do I want to do that? Well, because if I do the backpropagation, I'm going to be able to calculate the gradients of my error with respect to my model parameters. I'm going to say that again. I'm going to be able to calculate the gradients of my error with respect to my model parameters. What does that actually mean? Well, it means that if I change this parameter, right, for each parameter of my model, for each weight, for each bias, if I change it, let's say I increase it, what effect is that going to have on my loss? So there are two key things here. How sensitive my loss is regarding to this parameter. So if I change it a little bit, is it going to affect my loss a lot? Or if I change it a lot, is it going to change my loss a little bit, right? The sensitivity of that. In addition to that, it can also tell me the direction that I need to change it. So let's say if I increase this parameter value, my loss is going to also increase. Or if I decrease it, my loss is going to decrease, right? So once you have that information, then you can use an optimization method. Typically, the optimization method that we use, or at least the one that made famous the deep neural networks, is the one that is called gradient descent. So in gradient descent, you basically assume that that you have a little ball, and that ball is placed in a space, in a very high dimensional space of your parameters, and then you have the of your loss with respect to your parameters, and then that ball is trying to find a valley. So you want to find a point where you want to find a combination of parameters that is like well, you ideally want to find the global minima. You have imagine like a place where you have a lot of mountains, and you want to find the lowest point, the point with the lowest loss, right? And that position is defined by a certain combination of parameters. And then the model is gonna, but the model doesn't know where that valley is, so it's going to go here. Maybe it's gonna go to a wrong direction, the wrong place, and then you're gonna evaluate it again, right? And then say, no, I need to do better. So then the model would go to another place, right? And then eventually it will find the global minima. And then here we have the learning rule, and here the learning rule is basically how do we update our parameters. So here it comes to play whether you want to use your learning rate, whether you want to use momentum or something like that, right here. So we here just have the standard learning rule for gradient descent. Does anybody want to add something here of my hackers? No. Right. So then let me continue to the next part. So here we have the previous winners of ImageNet Large Scale Visual Recognition Challenge, which is a very, very, very large scale challenge. Regarding, I think it's roughly like 14 million images. And the objective of this challenge is to be able to classify these 40 million images into 1,000. I think there's a reduced set of 1,000 classes, and there's another set of classes that is much more classes. But here the question is, why do we want to use CNN still, right? So if you look at these models, they have plotted the top 5 error rates. So okay, so the top 5 error rate means that how often does the correct prediction fall in the top 5 probabilities of my model. So here you can see that there's a list of models. So the winner of 2011, the winner of 2012, all the way until 2016. And here,
Jose,
yes,
is it okay if you answer some question?
yes, sure.
So there's a question is are there any data limit like size in gigabyte or how many?
Good question. That actually depends on your system, on your hardware, because more specifically on your RAM, that is defined by your hardware, which is your GPU, graphic processing unit. Um, I think, if I'm not mistaken, NVIDIA GPU 1080 has roughly, I think it's either 16 or 32 gigabytes. I'm not sure which one does it have. So that means that how much data can you work with at the same time, right? Now with cloud systems, you can rent GPUs, like for example, like AWS or Google Cloud or Microsoft Azure. You could basically rent a piece of their of their supercomputer, right? And then that one has a lot of RAM. So is there a limit? It depends on your hardware, right? But yeah, who asked that question?
Kukuli.
Yeah. Um, yes. So, for example, here you can see that, but definitely in most situations, a laptop is not enough. Your laptop with one GPU would not be enough to do large scale computations, right? Like truly dealing with the big data, because the data can scale very fast. As you will see today in our experiments, we had to like downscale our data so much because videos, especially videos, right? You have a lot of images that are coming in, and that then yields for very high dimensional data samples, which is very hard for us to deal with because we are a lab, right? We don't have the amount of so extensive computational resources. But then there's tricks to how to most of the tricks are how can I deal with this data, right? That is in lower resolution, because most of the times you don't have enough computational power to be able to just push everything as very raw, right? So you most of the times you need to do preprocessing to deal with this data, either dimensionality reduction or making or working with gray images as opposed with RGB images, right? Or maybe working with instead of working with 1080p, you need to work with 400p because it's like it's too much, right? Especially as I mentioned before, that we need a lot of samples to be able to train our model, a model that can generalize well. So imagine you have a very high dimensional data, and you have a lot of this data, and it scales very fast, right? Because it's like multiplicative. And then and then the model also does some copying of the data to for the training. It's just a lot. So typically the most of the when you do projects like this and try to solve problems, how much can I reduce the dimensions of my data, right, and still get a good result? That's usually like the trick. But here I want to show the winner of the image large scale visual recognition challenge. So why do I want to show this? Because these models are models that are very good at seeing the world. They're models that have been trained on millions, like 14 million images, and they are very good to see the world. Even after 2014, you can see that they even surpassed human level performance. And what is very curious about these models? Well, at least from AlexNet and onwards, they all use the convolutional operation as their core technology. So the convolution is crucial for understanding, for machines to see the world as we humans see the world, and that's because they aim to mimic. They're designed to mimic the human visual perception system, right? They aim to look at the world as we humans look at the world, and we will explain why does that happen in the next slide. So, and another thing that you can see is that how much the layers, right, increase. So typically the layers, they are also correlated with the amount of parameters of the model, and you can see that after here, boom, we have just a bunch of layers that are being added to the model. So I think GoogleNet is another name for, or is the first iteration of Inception, which is a very famous network, and ResNet is also a very famous architecture of a network. And then this one is I believe is this is an ensemble model, but I believe this must be also like some probably it will be something related with the ResNet. So convolution is crucial, right? It's the core technology, right? It's the state of the art for image for computer vision tasks and image processing tasks.
Jose?
Yes.
There's another question from Sebastian. So the question is, how can we?
Welcome, Sebastian.
Okay. The question is, how can we optimize the data processing, editing, or erasing some layers? This is the case for some light version of some CNN and detector as YOLO. How is it possible?
So if I understand the question correctly, is how can I determine the number of layers of my network?
And how is it possible to obtain so good accuracy with laser layers?
Oh, good question, Sebastian. It is possible. That's actually a little bit more. So the first thing, how can I determine the layers of my neural network? Typically, or at least it's in my experience, you do that heuristically, or as other people would say, empirically, or as I would like to call it, just by by experience, right? Um, Now there's obviously systematic ways to do this. Like for example, you could do hyperparameter tuning, which basically you test, okay, if I add one layer, how does my model perform? If I add two layers, how does my model perform? If I add three layers, how does my model perform? Right? And then 4, 5, 6 until maybe whatever number of layers that you want. And then you would see the loss. What you want to see is the loss, right? Because the loss tells you, okay, how far my prediction is from the actual value. And then you would see that typically it goes like a curve, like this, and then you will find like a little valley, and then okay, at this point is the less. I'm getting the less or smaller loss. Then okay, at this point is the optimal solution, so I need to add so many layers. It is possible to get good accuracy with few layers. For example, let me show you the previous slide. So in this case, Google has 22 layers, right? It doesn't seem like that much. But here, this model is called Inception. The whole point of having the Inception is that it's like a network. It's called Inception if you have seen the movie, because it's like a dream within a dream, except that right now it's called Inception because it's a network inside a network, right? So what happens is that in each layer you have a little network, and then that's what it allows you to have very shallow networks, but very wide, because every layer is like a kind of like a different combinations of layers, right? And so these two have actually represented this ResNet and Inception have represented a big advancement in convolutional neural networks, because ResNet allows you to have a lot of layers and still get good performance. Like this is 152 layers, a lot of layers, and get good performance. And GularNet shows you that you can get like few layers but large, like but very wide, and get good performance. But the key here is the number of parameters, because whether you have a few layers or a lot of layers, the key in reality is the number of parameters, because the number of parameters is what actually defines the complexity of your model. A model that is complex can learn complex functions, right? A model that is simple will only be able to learn simple functions. I mean, if you have, assuming that you have enough data, right? Yeah, so in reality, it's the number of parameters of your model that determine whether the model could perform good, and also the data size, right? So just to yeah, so the convolutional neural network uses convolutional layers to convert the input from the original matrix of pixels to the extracted features, right? And then we will see why this convolutional operation is key. And then a CNN can be seen as a sparse spatial case of a fully connected network. So here we have a little animation of how does the convolution actually work. Maybe I think my assistant Jacob has a very good way to explain this one. Jacob, would you like to tell the audience?
Okay, so as shown in this animation below, and we're using a two-dimension convolutional neural network to explain how image data and convolute filter work in a convolutional neural network. So first, our output is image data. For simplicity, here we're using grayscale. So with the one value in each pixel. So here we render one value in each grid, and constant width of the image is the H and W. And here we're using a filter of size KW and times KH. And then we will doing the inner product curve with the filter values according to the size of the filter block, and study from the top left corner and of the output. So after all of the block are calculated, the result coming out and is displayed on this right. So the size of the output is the W minus KW plus 1 and times the H minus KH and plus 1. Thank you.
Yeah, sorry, my mic was off. So again, thank you, Jacob. So just to emphasize on what Jacob was saying, here we have an example of, in this case, it's a matrix. You can consider this to be a black and white image, right? With dimensions WH, width and height, and then we have a kernel, right? That's what also known as a filter of size K, W, and KH. So how does the convolution actually work? Well, I will get my little kernel, and then I will put it on top of this group of pixels, right? So as you can see, it will be here, then it will go here, and then it will go here. Let me then just bring my calculator out. Okay, so what's gonna happen? I'm gonna multiply each of these numbers with, I'm gonna multiply each overlapping number, and then I'm gonna add them. So for example, here is gonna be 5 times 1, 5, plus 10 times 0, which is 0, plus 9 times 1, plus 9, plus 4, plus 7, plus 5. Gonna give me 30. Then once I get that number, I'm gonna put that number in the position that I get my, where I found it, right? So in here, and then it's gonna move. And then as you can see here, it will do that for all the different positions, right? So you can see, for example, I want to stop. Okay, didn't stop. I want to stop it. Okay, here it will. This position corresponds to this number. This position corresponds to this number. This position corresponds to this number. And then in the end, assuming that you have a stride of 1, so assuming that you're moving every time just one little pixel, you're gonna get the output size is gonna be W, which is the original size, minus K, which in this case is 3, plus 1. That's if you have also like valid convolutions, right? And you're not applying like zero padding at the outside to make to keep the same size of the input. So here it is, the input is represented as red. We have a white kernel, and then the output is represented as red. So again, why, as I mentioned before, these networks aim to mimic the visual perception system of a human, because we as humans, we look at the stuff. We look at a picture as a group of pixels, right? So if these pictures are together, it makes sense that I analyze them together, right? Because as you saw when my assistant Rick was explaining the perceptron, that basic architecture of a neural network, like let's say, like, okay, let me go back to it. Here, you basically you can expand this into having more features, right? Like you could, for example, you can get your image, right, and then you can straighten it out, you can flatten it, and make a little thread and then feed the image through this network as well. But what happens? Then you lose the spatial information. Then you're not considering the pixels as a group, right? The pixels have the position of the pixels don't have any relationship with each other, and that's why that's the magic behind the convolutional neural networks, and that's why they tend to surpass basically any other architecture for regarding image processing tasks. So then that's why we decided to use that architecture, right? Since we have videos, an image is a 2D, right, map. A video is a 3D map with which is a series of images, So then that's why we use the 3D. Then right now we're going to explain the method. Okay. So as I mentioned last time, is it okay? I'm just gonna pause these videos because they're actually making me a little bit. Yeah. So as I mentioned last time, last workshop, on the second workshop, we discussed how do I collect data from the OCD, right, using the OCD, and also how to extract the finger trajectories, right, like the Euclidean distance of the fingers. So I also mentioned that the data that we have is collected from 2 healthy subjects doing the finger tapping test, and they have these stickers. So these are actually just GIFs that we made of the data. So we have subject 9999974, and then we have his right hand, her right hand. So her right hand on the right. So these 2 are from 9974, 99. Yeah. So the 74 is here, and then 999. 99975 are on the bottom, right? So this is a different subject, and you can see that, for example, the right hand is filmed with the left camera to get the opposite view, and then the left hand is filmed with the right camera. Okay, and then they're just doing that test, right? And then you can see that this is how they're doing. It's just pam, pam, pam. Just what we instructed them in what we wrote in a protocol. And so unfortunately, so today we're going to focus on coding the CNN to analyze these trajectories, to predict these trajectories, and we would have unfortunately we aren't available to share our data due to restrictions stipulated in our IRB. I think IRB stands for could somebody remind me what is IRB? But it's something board. Institutional Review Board. Yeah, so basically it's a set of as I understand it, it's a set of rules that we need to follow in order to collect human data. So we need to, one of these restrictions is that we need to keep the data anonymous, and we're not allowed to share this one, right? Because it's data of Parkinson's disease patients. When I do the code, I'm gonna use this data. You don't have this data so far, but I encourage you that if you would like to follow our data analysis, please check out our second hackathon to see how can you extract your own data, right? You might need to change. You might need to find some stickers or something like that, and maybe need to change the value of the colors. But then you should be able to extract the Euclidean distance of your fingers as well, and then extract the from the trajectories, right? So we followed a jackknifing resampling scheme to sample multiple videos from our 4 recordings. So let me explain what does this mean. So when I received the video, I received this, right? So the video is, like I told you, a collection of images, and these images are in RGB, right? So let's say I get the first video. So this here I'm explaining what is the processing pipeline that I follow to get a lot of data samples that are relatively low dimensional. So as you can see, the data from the OGD is 1080p, right? So that's why it has 1080 times 1920. And then we have 6 seconds of data, 6 seconds of the person performing this at 60 FPS. So we have 360 frames. So you can imagine this is 1080 here, 1920 here, and then 360 of this. And I have 3 of these because they are encoded in RGB, right? Then the next part is, okay, I want to discard all of the stuff that is not hand. Why do I want to do that? Well, there are 2 reasons. One is because I want to discard everything that could introduce noise to my model, right? Because I want the model to look at only what is important for predicting the trajectories. It doesn't need to know about the chessboard. It doesn't need to know about the iPad. It doesn't need to know about any of that. It only needs to look at the hand and more specifically like the stickers, right? Because we calculated the stuff from the stickers. Then another reason is because I want to make all the hands look similar because subjects have different size of hands, right? But if I resize them into the same size, so that means that their hands look different, or maybe they will put their hand closer to the camera or a little bit farther. So then I need to resize them. I want to resize them all the hands to the same size. So here, when I crop the hands, they end up having some value of H and W, and this value is obviously between 50 and 1080 for H, and it's between 60 and 1920 for W. Then I have still like 50 times 60 times 360, right? And then have 3 of them because they're still encoded in RGB. So then I start thinking, right, okay, but I actually, for predicting the Euclidean distance, I only need to know, I mean, the Euclidean distance is, I can see it by how the fingers open, right? The color is not an essential thing. It's not an essential information for me to predict the distance because I can, even if it's black and white, I know, okay, this is opening, this is closing, right? And assuming that the network can perform better than me, the network should also be able to know, okay, just from the grayscale image, how are the trajectories, right? So it makes sense to me to make it grayscale. And now look what I did. So look how many, I basically decreased my data size by 3 here. And this is the whole recording of the video, right? So now I need to get multiple little videos from this 6-second video. And these little videos, right, are what I wanted to be half a second. And I will explain why I choose half a second and not 1 second or 2 seconds. And then I use a jackknifing resampling scheme. I think maybe Rick, would you like to explain what is a jackknifing?
Yeah. The jackknifing is, what jackknifing do is you will random pick a number, and the number will select the next 30 frame. So you can see here the 300 times the 50 times 60 times 30. The 30 frame is from the jackknife resembling, and because we have full video, so in the end we will have like 30 frames for each data, for each subject, for each hand. And yes, that's jackknife.
All right. Yeah.
Is
So
that too simple?
Yeah, jackknifing concept is actually quite simple. It could be stated in other words as sampling without replacement. So let's pretend I have a bag, right? So I want to get little videos. So I'm gonna put a lot of numbers in a bag, right? I have a magical bag. I'm gonna put a lot of numbers in this bag, like a lottery, something like that. Then what am I putting in? What do these numbers in my bag represent? Well, they represent the starting frame of my video snippets, right? So for example, let's say I pull a number from my bag, I get a 14. Then my video snippet is gonna be 14 is gonna be from my original video, frame 14 until 14 plus 30, which is 44, right? Let's say I pull another number, wow, 35, right? Then the next video snippet is gonna be 35 until 65, right? Because 35 plus 30, right? I'm gonna go here and then look for that video snippet. I'm gonna copy it into another sample, and then I'm gonna do that 300 times. So I'm gonna pull from my bag 300 numbers, right, at random and without replacement. So I basically, if I pull a 3, I cannot pull a 3 again. That's to avoid having repeated data samples, right? I don't want to introduce 2 of the same samples in my model because not really useful, right? And then I'm gonna do that for 300 times, and then I'm gonna do the same thing for all of my 4 videos. So I'm gonna end up with 1,200 samples, and each sample is a 50 times 60 times 30 times 1. So it's a 50 times 60 because of the size, is 30 because it's 30 frames, right? And then it's just 1 because it's just on a grayscale. So yes, another thing that I did was I normalized the Euclidean distance between the fingers and the velocity to be between 0 and 1 using a min-max normalization, and that makes sense to me because since I crop the hands, right, and I resize them, then all the hands look the same, or they look as similar as you could make them, right? So then they must have the same aperture between the fingers and roughly the same velocity, right? And then for the classification of whether they are opening or closing, I just look at the entry that they have there, and I just make them 1 if it is opening and 0 if they were closing. So let me show you what do I have. So when I get this is the labels. These are the labels for subject, for the video of the subject 999. I don't know if you can see a 74 for her left hand. And then what I get is just the index of it's a spreadsheet, right? It's an index of the item. Then is the time, the position of the thumb, which is the position, the center of that sticker. Well, I think it's the blue sticker. That's defined by X thumb, Y thumb. Then also for the X index, Y index, it tells you the position of the index finger. And then this one, this distance, so it has 1, 2, 3, 4, 5, 6, 7, 8, 9. The 7th column tells you the distance between the 2 stickers. And then the condition tells you whether the fingers are opening or closing. And then the velocity, it tells you how fast are they moving, right? And I basically normalize these 2 to be between 0 and 1, and then I just make this one 0 if they are closed, and then 1 if they're open. So what does this look like? It looks like this. So for the Euclidean distance, you can see that, okay, this case is like closing, and then it open and close and open and close, and then I start to a little bit open again. And for the open close, you see that as it reaches this local minima, so it's closing, right? At the beginning here, it's closing. As it reaches local minima, boom, open, it becomes 1, right? And then it reaches this peak again, and then boom, close, and then open and close. And for the velocity, then you can see that here is moving slowly, and then as it's moving fast, my velocity also goes fast. And then here is going down, right? Because it's not moving very fast until this part. So this part is where the fingers are closing very fast. So then my velocity also has this spike here because the velocity is increasing, right, very, very quickly. And another thing that I would like to make notice of is that since we remember that last workshop I was talking about what do the physicians look at when they're assessing the motor function of Parkinson's disease patients, is that they are looking at how many hesitations, how many interruptions, or maybe like hesitations or halts, impediments does the subject display when they're doing the test. So for me to know that, I need to have an observation window that is at least one cycle, right? So that I can see, okay, yeah, here he didn't do it. Now for this case, the data looks very similar for most of the videos because these subjects are healthy, right? So they can perform the test without any problem, right? If we had the Parkinson's disease patients, we will be able to see like a little hesitation, and we'll see like this, maybe some bump here in the Euclidean distance, like going down and going up very quickly like that, which will be more interesting. Okay, so then lastly, I would like to just briefly discuss the structure of a convolutional neural network, and then we will take a little break before we do the coding part. So this network architecture yields roughly 5.2 million parameters. So there are 5.2 million weights, right, that we're trying to solve for. And then so basically it looks like this. So I have my input shape. Remember what I said? It was 30 frames. Each frame is 50 times 60, and then I have they're grayscale. So they only have it's only one. Then I'm gonna apply a convolutional 3D kernel. This kernel is going to reshape my input into something smaller, because remember when we were discussing the convolution, that the convolution actually creates the maps that are smaller in dimensions, in spatial dimensions. So it does that. So if you remember correctly, it was the original. So the new size is going to be the original size minus the kernel size plus 1. So in this case, it's 30 minus 7 plus 1 is 24, right? And then 50 minus 9 plus 1, 42. And then 60 minus 11 plus 1, 50, right? And then I have 8 because I have 8 filters. I will explain. I have another figure later to be more specific. But the point is that I'm going to apply convolution. 1, 2, 3, 4, 5, 6 times, right? And then I'm going to get this volume that is 6 times 14 times 12, and then I'm going to get 256 because here I have 256 filters. Then I'm going to do a global average pooling. So what does that mean? A global average pooling will look at each of these 6 times 14 times 12 cubes, and then it will calculate the average of that cube, and then it would return me that single value, that scalar. And then with those, so that's why I end up having 256 things, scalars, and then I just finish it by having a dense layer, which represents my prediction layer, my output layer of 30, because what I want to predict is all of this. I want to predict all of this. So I need to have 30 numbers, right? They're represented by each of the 30 neurons in my output layer. So here I just have a slightly better visualization, but obviously without being very specific. So what I have here is that my video is a cube, right? It's 50 times 60, and it has 30 frames. And then I'm going to apply convolution 3D. So remember, for convolution 3D, the kernel was a matrix. For convolution 3D, the kernel is a cube, right? Then I'm going to apply this kernel here, boom, and then I'm going to get another feature map, right? This feature map, as we discussed, is smaller than this one, right? And then each of these cubes is going to give me a different feature map, right? And that's why, so that's why this, let's say, milk color cube is the output of me applying the convolution of the original image with this filter. This trim orange is the output of me applying this filter with the original input, and then I have 8 filters, right? So I also have 8 maps, and then this dark orange is gonna be the output of me applying the convolution of the original image with the last filter. And then I'm going to continue to apply the convolution until I end up with 256, until I end up with this array of cubes that are 14 times 12 times 6, and they are 256. And then I'm going to apply global average pooling to get the average of this little cube, right? This cube is going to give me, well, I'm going to calculate the average of this cube, which is going to be one number. I'm going to put it here. And then I'm going to have also 256 numbers here, right? And then I use the dense layer. And the dense layer is the same thing as my assistant Rick was explaining at the beginning, which is everything is connected and every feature is the linear combination of the previous feature. And then this is going to be 30 in this case. So 30 because it is every element in my output sequence, right? Okay, so here we're gonna take a 5 minutes break before we get into the code. Here you are able to check our Google Colab code. Feel free to, maybe you can write in the chat, Rain, where can they find the presentation? And also you in the presentation, you'll find this link. But for right now, we will take a roughly 5 minutes break before we dig into the more technical stuff. I hope that you guys are ready, and we will look forward to learning together with all of you. So take us to break. Go. Okay, so welcome back, everybody. As I promised you, we have the coding part of our workshop. So here, I just want to show you very quickly what do we have. So here we have let me make it bigger. The CSV files. Is my thing clear? Is my window clear here? And then you have okay, let me drag this here. So this is the video, right, of the subject performing the test. It's roughly 6 seconds. And then each video has their respective CSV file that tells you the distance, the velocity, and whether they're opening or closing. So this basically I come here to my Google Colab, which you have the link in the presentation. You will see a copy of this one, and then you load all of this data here. And yeah, so then these are contributions to the OpenCV AI completion for 2021. Our team is the National Chen University's Parkinson Disease Quantifiers, which is a mouthful. And then here we will use a 3D CNN or convolutional neural network to predict the Euclidean distance between fingers, velocity, and whether the fingers are opening or closing from video snippets of the finger tapping test. Okay, so the first thing I would like to mention is that due to time restrictions, I will only do like the Euclidean distance of the fingers. The velocity and whether the fingers are opening or closing, they are very similar, right? You just need to change the index when you import the label. So I will explain a little bit. But the first thing is to import the required packages. So these are all the packages that I need. I need TensorFlow, I need NumPy, I need Keras, I need Computer CV, and PyPlot, Pandas. Then I need to define the path of the video data and the trajectories. So the trajectories, I refer to these CSV files. And this should be defined by subject ID and then which hand. And here we have the videos of the crop hands with the raw trajectory. So the trajectories are not normalized yet. I need to normalize them. So then I have my path and my file name. So this define which subject and which hand. Then we want to subsample from our video recordings to obtain video snippets. Okay, so all of the preprocessing step that I discussed previously is on this chunk of code. So all of it with the reshaping, the transforming into 50 times 60, making it grayscale, and jackknifing is all in here. So basically, what I do is that I create 2 empty variables that are gonna store my video snippets in X and my labels in Y. I define my sample length, which in this case I want to be 30 frames. That equates for half a second, and then I want to get 300 samples per video, right? And then I also define my size. So then here is the standard procedure to how to read videos using OpenCV. So you are able to use this one, whether you know, when you want to read any video. So you have you open the video capture and then you tell it which video do you want to look. So I'm gonna do this for all the files. So it's going to look for the first file plus hand. So it's gonna look in this case first this one, then this one, then this one, then this one. Okay, one interesting thing that I do is that since I have the hands like are opposite, right? So if, for example, if the name contains this string that is right, I flip it so that all of my hands are facing the same direction, right? So I only get the left hand view of the subject, basically, right? Because I flip the right hand, I mirror it, and then I for each frame I append their grayscale value. So OpenCV reads the stuff in BGR, and then I append that into some array that is called gray data, and then you can see that if I run this one, it's telling me that I have 359 instead of 360. I think this is because I think one frame is lost when I was doing the cropping of the hand. But you have the gray data is 359 times 50 times 60, right? Because as I told you before, I reshape it into this smaller size. And then for my data frame, I have I read all of this CSV file. Okay, so let me do this. What is vf.head? So it's gonna show me. Oh, because I do. So this, let me read this because I made it a numpy, right? Yeah. So when I read this, it's telling me that I have 1, 2, 3, 4, 5, 6, 7, 8, 9 things, and this is the same thing as we have seen on our CSV file. Yeah. So then I convert it and I discard the last one because this is the one that I missed. And then here is sampling without replacement. Get the training data by splitting the data randomly. Sampling without replacement. So here the samples IDX is a vector that contains my starting frame of the video snippet, and this one is defined by numpy random choice that will take items from 0 up until the length of my array minus the sample length, and then it will take n samples. So how does this actually work? So let's pretend like I told you that I have a bag. Instead of this one, I'm going to have a bag that contains little papers, and the papers have numbers from 0, 1, 2, 3, 4, 5 until 10. And then I want to pick, let's say 4. Then you will be able to, what it returns is just 4 random choices, right, without replacement. You will see that the numbers you never see the same, or let's do a larger one, let's say 8 or 9. I'll pick from this bag, I pick 9 numbers. So you see these numbers are never repeating. There's never a 2 2s or 2 3s, right, because we have done sampling without replacement. If I did sampling with replacement, it will be called bootstrapping, right? So then I will be allowed to pick 2 trees or multiple trees. But then that's what we have done for right now. So let me just run this one again. It should be fine. And then now I want to split my data into training and test sets. And I do that by using this function. I use model selection, train test split. I split my X, right? And I expand one dimension because I need to specify for TensorFlow that this is a grayscale image by giving this 1 at the end. And then I also split my Y so that you split them together. And I give it a test size of 0.2. So that means that my training set contains 80% of my samples, and then my test set contains 20% of my samples. So here you can see that this my X train, the shape of my training samples, training videos is 960. That is because this is 80% of 1,200 is 30 frames. 50 times 60, right? That's the spatial dimensions of my frames, and it is 1 because it is a grayscale image. And then for my Y train, for the labels of this one, I had the same number of elements, and each element contains 30 things, and then these 30 things can be anything from the distance, open, close, velocity, position of the fingers, and so on and so forth. And then the X test is 240, so this is the 20%. So if you add 240 plus 960, it should be 1,200, and these are the same shape. It's very important that these four numbers are the same four numbers here. Then I define my min-max norm that is gonna bound my values to be between 0 and 1. I'm gonna use this one for the velocity and for the Euclidean distance. And then I have my binarized open close. So this one is just going to look whether it is closed, and then it's going to append a 0. And if the thing is open, if it says open, it's gonna append a 1. So okay, so here I just plot the sample one. So you can see that here is closing. It comes here to the local minima, start opening, right? And then we can see a 1 here. And I already demonstrated this one from before. And then here, this is just a little trick to see how does the video relates to the data. So this is just plotting the different frames on top of each other. But here you can see that basically this thing starts closing, opening, closing, opening, closing, opening. So you will be able to see 3 closes, right? But start from open, close, open, close, open, close. Should be able to see that. Oh. So open, close, open, close, open, close, and should finish in this next opening. There. Was that able to be shown, guys? So this matches perfectly with the labels. It's very important to observe, does my label matches my sample, because otherwise then you wouldn't be teaching the model the correct things, right? Okay, now this code is actually very short. So then we define the model structure. So we use Keras sequential API to define this deep learning model, which is defined like this. And then you define how many filters you want to give it, the kernel size, you want to use which activation do you want to use. We have ReLU, which is the one that rectify linear unit, that is the one that we shown. We have our dense layer and sigmoid to bound the values between 0 and 1. And then we tell this model to compare the prediction and the ground truth using the mean squared error function, and to optimize using the AdaMax optimizer, which is a variant of gradient descent, just a little bit better. So okay, so then I define my model. Then I can tell the Colab to give me my model summary. And then here it tells you the information of your model. First of all, it tells you if your model was able to be created correctly, right? Because otherwise you wouldn't be able to have model summary. And it tells you the number of parameters at each layer. So in here, this is the number of parameters are determined by how many maps you have on the previous layer, the number of filters that you want to apply, and also the size of your kernel. And then most importantly, it tells you the number of parameters that you have, total trainable parameters, which in this case is roughly 5.2 million parameters. And then once you have that, then you're able to fit your model by using this line. So you tell the model, okay, take my training samples and my normalized labels and train 50 times. I want you to go through the data 50 times. And every time I want you to take a batch size of 8, and I want you to validate on my validation data. And then you would run it. Boom, and the model will be running. It will take some time. Well, this process actually takes quite a lot of time. So I'm gonna stop this one. And then here I just save the model and train it. So in this case, I have some pre-trained models. If I can just load them here. Here I'm loading the pre-trained model that I trained yesterday for the fingers. This is quite a big file, so it might take a little time to load. But let me just explain what I'm gonna do. So I'm gonna load the model, right? This model is gonna be fairly good. Then I'm gonna get the predictions of my model, and then I'm gonna get the residuals. Sorry, the errors, which is the mean square error scores for the validation data set. So my validation data set has 240 items, 240 elements. That means that I'm gonna get 240 things. And then I also tell it to give me the average of the residuals. Just wait a second because it's still loading, because it's quite a large model. Then I will be able to plot that. So these are all results that I have been getting. So this is just the distribution of the validation errors. We want to check the distribution of the validation errors to see do I get a sample that is totally different from the others, and it gives me a large error. Is my error normally distributed? Is my error right skewed? In this case, it's right skewed because the minimum value that you could get for the loss is 0, right? And the model is performing quite well. So the model has most of the samples here, which kind of show like a bell curve, but it does have some samples that are a little bit, let's say, strange or irregular or outliers. And then they have, for example, just one sample here, 2 samples here, right? But most of the samples are basically in this bell curve. I think it will be similar from this model that I'm doing. Wow, it's taking quite a long time to load. And then I will be able to, I will get the minimum residual, which is the best case, right? Because the lowest error corresponds to the best case, the median case, which is the error that is in the middle, and then the maximum error, which is the worst case. And I will be able to plot how the prediction. I think typically it's good to look how does the model predict. In this case, the prediction is quite good here. I would say. I think that it fits this line very well. Even on the median case, it fits this line also quite well. But on the worst case, yeah, it seems to not perform well. I think it's interesting to see, like, when the model performs well, does it actually, I mean, when the model performs the best, does it actually perform well, right? When the model performs the worst, does it perform bad? In this case, it does perform bad. But more importantly, how does it perform bad? In which case, it does. What's strange about these samples that makes that model be bad, right? Maybe it's the label that is wrong. Maybe it's the sample that has some irregularities. In this case, I can tell you that this sample is very strange. Why? Well, you could see that typically you would expect to see maybe one cycle, right? You would expect to see maybe what, maybe 2 cycles, right? Like this one. This is probably like the most common case. This one also can see like 2 big cycles, maybe, and then half of one here, half of the other one there. But this case, it definitely looks very strange. Why? Because you can see it's like the credence is like so much. I have 1, 2, 3, 4 cycles. I don't think that in many cases I will get 4 cycles for a half a second. And in addition, this drop here, this sudden drop looks very strange, because it means that it just for basically for a couple of slides of a couple of frames, it became very fast, right? So I think that in this case my model performs poorly, not because the model is necessarily wrong or bad, but I think maybe the trajectories were not extracted the best here. Maybe there contains some noise. Maybe it was blurry that we couldn't see the stickers, right? And we couldn't actually get the trajectories very well. In this case, I think it was probably blurry because my model also performs like shaky here. So this kind of analysis allows you to explore the data and kind of like understand how is the model working, right? Which is the most interesting part for me. So this model is taking so long time to load. Okay, let me come back to it later. So then let me move on to the results part. So this is what we did for our submission. So we evaluated the network using an 80-20 split, train test split, and each model was trained for 50 epochs, and the version of the model at the last epoch was used for calculating the error distribution of the validation samples for analysis. Why we trained 50 epochs? Well, we wanted to find a nice compromise between actually finding a model that represents a good solution to the problem, but at the same time, we didn't want to spend so much time training the model, right? Because we believe that more training after this one would just represent a marginal improvement to what we have. So you can see here, then for this part, so then one thing that we did since the submission was that we trained our model for more epochs. Maybe Jacob, could you tell the people why?
Yeah. So basically, the reason why we training to 200 epochs is because the model we submit to the OpenCV condition was training for the 50 epochs, but in fact, the observation losing and the validation loss was still decreased. So we were curious about how good a model can be. So we training 200 epoch and to see the performance. So yeah, that's all. Thank you.
Yeah, so as Jacob was saying, we trained 50 epochs, right? But we still see, let me go back to the previous slide. We still see that all of these trends seem to be still on a decrease, which represented that we find a good solution to our problem, but we didn't find the best solution due to the time limit and computational resources that we had. So we wanted to see, like, okay, if we had more time, right, and we could train them more time, more epochs, could it be better? And then the answer is yes, but that's just marginally. As you can see, it did improve a little bit from 50, but considering that 4 times to train and it just improved marginally, I think we find a good compromise for and that's the same case for all of the models, I would say. Then we have the error distribution, which I mentioned before. They are all right skewed. That's because the minimum error is 0, right? So, and the model most of the time perform very well. And there's just some strange cases here where it doesn't perform very well, but I already explained to you why that is the case. It's not that the model is bad or something like that. And another result that we have. Okay, so I already showed you what is the. We also have the best, median, and worst error. So I show you the one for the distances. I'm gonna show you the ones for the other ones. Oh, so yeah. So for the distribution of the errors, you can see that basically the the yeah. So the open and close one have this yeah. So I would say that the open and close are probably the um, yeah, I think these two should be flipped. This I think this figure should be here and this figure should be here. No, so yes, they're all right skewed, and but this figure seems to be much more has much variance over these samples. So then yeah, so this is the best, median, in worst cases for the ground for the distance, and these are the best, median, and worst prediction cases for the opening and closing. So here we can see that the prediction is not all the time 1 and not all the time 0, but okay. So also another thing that we plotted here was this red line. This red line represents the typical boundary decision for a binary classification. So if you're trying to classify whether it's open or closed, right, and you give it a score, typically what people would use to determine if this is open or closed is, okay, if it's more than 0.5 it's open, if it's less than 0.5 it's closed, right? So then here you can see that, yeah, for the worst case, for the best case is pretty good. Like all the time that this is open, it always gives you a value that is more than 0.5. All the time that it is closed, it gives you a value that is less than 0.5. Here it starts to lag a little bit, for example in this case, and yeah, and then for this case it is the worst, right? And I think also because there's this very quick set of frames, and then for the velocity, I think it performed quite well on the best case, but it didn't perform so well for the median and for the worst cases. And I think that kind of gives me an indication that, yeah, the velocity probably is a harder function to learn than whether it's opening or closing or the distance. And I think it makes sense to me because the velocity is the derivative, right, of the position. So that's why I think the model has probably harder time to learn this function. Okay, so then another experiment that we did was to change the number of parameters by adjusting the number of filters in the 3D CNN. Maybe I think Rick could explain what did we do here.
Okay, so as we know, the number of parameters determine the complexity of the model. So if we have a simple model, need to learn a simple data, right? So, and our model here is not, maybe it's not very complex, but we are interested in how will it perform if we try to make it learn more parameters. So that's the reason why we try to do this.
Yeah, sorry. What we just is that we have 5 different models that are defined by I, right? And then we basically have a so when I is 0, I have my most simple model, which means that I have the model with least amount of parameters. And then when I is 4, then I have my most complex model, meaning that I is meaning that I have the most amount of parameters. So you can see here how does the trend look like. So basically all of the so then we trained all the models for 100 epochs, which is usually more complex models. You should train them for more epochs to reach convergence. But in this case, we decided that we wanted to compare all of them in the same level. So we just trained all of them for 100 epochs, and then we can see that all of these show that there's an increase in performance by showing a decrease of loss as we increase the number of parameters. So here I would like to notice that these values in the x-axis are in log scale. So there's a huge amount. There's a very large difference between the first and the second item, and then it's a larger difference between the second and the third, and so on and so forth. Even so, this means that if we had more parameters, the network could learn better these functions. And I think that makes sense because we're trying to predict trajectories. So it's actually quite a complex thing that we are asking the model to learn. But we need to think about the training time, right? That we are requiring from this model. Could you so in this case my assistants were the one who were training this. Could you guys give an approximate of how long does it take to train this model, and how long does it take to train the more complex model, like say for one epoch?
I think for first maybe take, I don't know, 40 minutes or 30 or 1 hour, maybe 30 to 1 hour, and the most complex take me maybe 16 hours.
Oh wow. Yeah, so that's a huge difference. So this is the kind of like the balance, right, that we need to deal with. So I think that the model that we chose represents this needle point, if I'm not mistaken, right? Our model culture that we show in this presentation is this third point, right, guys?
Yes, right.
Okay, yes. So it takes a rough, if I'm not mistaken, it takes for 50 epochs, it takes like 50 times 200 minutes, so for 100 epochs it would take 200 minutes. Yeah, so that's like 3 hours something. And then let's go into the conclusions just to finish up. So what we demonstrate is that it is possible to predict the distance between fingers, velocity, and to distinguish between opening and closing motion from the video data. That means that predicting the UPDRS scores from the video recording should be possible, since these scores depend on these metrics. However, one of the important things is that in order for us to obtain a finer scale of the differences, we need to consider what is called micro motions, because the Parkinson's anticipation, their motions are very small motions, right? That are very difficult to observe. And to deal with these micro motions, we require equipment that allows us to record the data in high spatial and temporal resolution. And we also think, as we mentioned last time, which we attempted to do, is we think the spatial AI can be used to calculate the depth of the points we track and to obtain their 3D position and the distance between the fingers, the velocity, and other metrics more accurately. And this represents an increase in robustness on the relative position of the hand of the subject with respect to the camera. And why it is important? Because as I told you before, if the label is wrong, that model will learn the wrong things, right? And it will be suboptimal. So we need to make sure that if the fingers are separated by a certain amount, that amount is really captured, right? And what happens is that it depends a lot on how the subject places the fingers in their screen. If we can currently can detect it accurately, if we had the 3D information, the depth information, it will be much more accurate and much more robust for us. And then we believe that the OAK-D represents a significant improvement to our data collection system because its camera allows us to collect high-quality data. In addition, its accelerated computer vision processor allows us to extract vital information to estimate the metrics associated with gradual deterioration of motor function of PD patients, which will help us to improve on our existing work. And I think that will be the end of my presentation. I would like to thank all of you for joining us. I would like to thank my team for working very hard on the presentation and on the code. I think we will open up for a round of questions.
Yeah, we have a Q&A session in Google Meet later. And yes, now the session is in our Google Meet. We'll be back in 1 minute, then we'll start our Q&A session.
Yeah, so welcome, Sebastian. Could you repeat your question? I think we're talking a little bit offline.
Okay. So let me explain it. Thanks for your invitation, first, to all of you guys there in Taiwan.
Thank you for joining.
Thanks a lot to you. Thanks for the presentation. Well, actually, there exists a lot of enterprises that make some that give to us, to the CV community, a lot of annotation services with the addition to develop the models for a lot of tasks. So there exist some companies just like RoboFlow or SuperAnnotate or Pixelia. But not all this company give the option to the user to setting the hyperparameters. And for the beginners in this world of artificial intelligence, the first step to overclose is to know what the fuck are these hyperparameters.
Sure, definitely. No, you're completely right.
So can you make some resume or summary about the characteristics of these hyperparameters and how it is possible to us as users set the best value to these hyperparameters to develop our model?
Yes, that's a very interesting question. That's the problem that that everybody faces when they are beginning. So let me so I cannot share my screen right now, right? Okay. So let me go back into my presentation and just show you again. So the first thing, for example, let's say that we are dealing with convolutional neural networks, right? The first thing is we want to convolve this with this, right? So this tells you, or maybe a better idea would be to show you the code. For example, when I set when I'm creating my model, right, it asks me for these things. It wants the number of filters, right? It wants the kernel size. These are crucial because this basically tell us how many parameters am I going to have in my network, right? So the kernel size is this one, right? So remember that the kernel defines the size of the cluster that I'm going to look at, right? And then that you can have multiple of these. So when you have multiple of these, then you can have different eyes, for example, like different stuff that look at your data. That's the first thing. That's one of the crucial ones. The next one is how many layers, right? The number of layers that you want to have. So the number of layers is also crucial because they kind of like tell you like well, it's important up until a certain point. After a certain after another point, it doesn't really affect that much. But it kind of like, because the features of a neural network are built upon the layers of the previous feature, right? So for example, like, let me show you. So if I can go back to here, so these features, right, are built from the raw features, and then these features are built from the second array of features, right? That means that, so what does this actually translate to? What does it actually mean? This means that these ones can capture very simple stuff. So imagine I have my CNN, right? What kind of stuff would my CNN pick at the first layers? It will pick very simple stuff: lines, horizontal lines, vertical lines. Okay. Now, what kind of stuff can it pick on the second stuff? So okay, so it's building up on vertical lines and horizontal lines. Maybe it can tell me diagonal lines, right? Maybe it can tell me gradients, right? Like if it's going from black to white. And then you build up on those features, right? Until if you have, for example, like very deep, the deeper the layers, the more specific the stuff that you are looking at. So for example, maybe at the latest one, it will be able to look very complex structures like eyes, or it will be, or nails, or something like that, right? So that's then another hyperparameter of artificial intelligence. So the first for convolutional neural networks, so the first parameter is how many filters do you have per layer? What is the size of your filter, right? How many layers do you want to have? Another key one is which activation function do you want to have? So here we have ReLU. So ReLU has been proven to be the state of the art for activation functions in most cases. There are variants of ReLU but most of these new ones, they are actually built upon this. So because these are important because they kind of like they kind of like define what are the ranges of your values, right? For example, sigmoid bounds your output to 0 and 1, right? ReLU just bounds it to be a positive number. TANH with another function is very similar to ReLU, but instead of 0 to 1, it would be negative 1 to 1. So that's another thing that you need to consider. The next thing that you need to consider is well, let me look at the code. What else did I consider? Whether you want to have the normalization in between, right? Typically, it is good to have normalization because that can allow you to have your values in the same scale. So then your parameters can be in the same scale as well, and it can help on the model converging faster. Yeah, there's there are many more, but the ones that I believe that affect the performance the most are these ones, right? And if we could just wrap around everything, I think it will be the trainable parameters. This is the key one, right? This tells you, okay, my model is very complex or not. How well can my model? What are the complexity of the functions that my model can learn, and how much data do I need, right? And then that's the first part of your question. And then how can one find the best combination of hyperparameters? Well, that's what I was mentioning. I think at the beginning is you can do a hyperparameter search. Okay, so basically you basically find, well, there are many different ways to do it. You typically do like a grid search, right? So it means that you start, for example, I said my activation is like this, and then I just vary my number of layers, right? And then I want to see how does this look at, right? And then you look at what the value that you want to look at is the loss. So then that actually takes a lot of a lot of computational power, as you can imagine, because you need to create a lot of different model versions. And in this case, we have done a train test split. There are, for example, other ways to evaluate the model that are probably more robust, like, for example, K4 consolidation. That is very good and very, I think, in my opinion, is probably one of the best ways to evaluate the model. But it takes a lot of computational power. And the trick is that, it's not necessarily to find, because how can I say? It's what is important, right? I could spend a lot of time and effort in trying to find the best combination, but that combination it might be the best, but it might be just marginally best than if I just come up with a solution heuristically, right? But the point is that you need to know which ones affect the most the performance of the model, right? And so yeah, and then also so one of the things that we focus on is to, if you choose, for example, if you choose here, so we take a look at this plot, right? If you can choose the correct learning type and you can choose the correct architecture, you're already, I believe, probably 70% done with the work, because this is if you can identify which is the correct thing to use, then finding the best iteration of this thing, it can help you, but it will not, how can I say, represent a huge improvement, right? And these ones you can use it by, it's just understanding the literature, how people have people aim to solve these problems, and just look at what other people have done, right? If I can answer that question, yeah, I think that's how I would like to say.
Yes. That was a very good answer. So thanks a lot for the answer.
Do you have any more questions, Rain?
We do have another audience. Unfortunately, I couldn't pronounce his name. Do you have any questions? If you have any question, and yeah, maybe you can also type in the chat if your mic have some problem. Or maybe Sebastian, you have more questions?
Yes. Thanks. Well, in the presentation, I made some question about the how to editing the layers, or how to erase the layer to obtain a more lighter CNN model. But when we talk about the setting of the hyperparameters, how this economy on the number of layers for the light version of YOLO or another kind of CNN detector, how can affect the number of layers to the improvement of the learning rate when we set these hyperparameters. In other words, with the right hyperparameters and lesser layers, you could obtain better models more faster, or not necessarily?
With the right hyperparameters and less layers? It's a good question.
Yes, because you can see, excuse me, when you compare some light version of YOLO,
Yes.
You lost some accuracy on the detection,
Sure.
but you have a more accelerator frame processing.
Sure.
But the accuracy drops down.
Yes. But it's still good. If I'm not mistaken, it's still pretty good. And so the point is that these models, you can see that more parameters means that I need to multiply more stuff together, right? And to multiply this, add that more times, and that's what the layers do. And especially the layers, if more layers means that you have more process that is not sequential, because like I said, right, the output of a layer corresponds to the output is made from the output of the previous stuff, right? So I need to wait for that stuff in order for me to do this, then the next step. So it's not parallelizable, as we call. So in case where, for example, you want to have like a edge AI where you want to install the YOLO on a camera, yeah, that will make the system lag a lot, right? So there are different ways. So if I'm understanding, it's like, how can we compress the model? Is that something that you want to ask me, like, or what is the how is it possible to
Yes, yes,
compress the model?
yes. How
So
to compress the model with the lesser layers,
man,
but with the better
that's a very
hyperparameters
interesting.
values.
That is a whole new. There is a field in itself in machine learning, and that's a very interesting field. So, well, one of the ways that you could do that is there's this model compression technique. Model compression is called is the name of the field. Model compression aims to create a model that is smaller than the original model, right? And equally or similar performance. So one of the most interesting techniques that I can remember right now is that you basically have your model, right? And then your big model, basically is like a teacher model, and then you have a smaller model, which is the student model, and then the teacher provides the labels for the student, and then the student model just learns from that one. That's the most interesting one, and then you can obtain a smaller model. However, if you have, for example, you have the pre-trained YOLO, right? Because usually that's what happens. I go to the internet and I download YOLO, right? I cannot delete the layers because the output part of YOLO depends on the last part, right? So I cannot delete that one. So typically what people do is to create a student network. There are several techniques to compress a model, but so far, to be honest, I only remember this one because it was the most interesting one, the teacher-student learning strategy for compressing a model. You could quantize the model, right? Instead of working with floats, you could work with integers. That will make the processing speed go faster. But so far, yeah, I only remember these two, to be honest. But that's a very interesting field, definitely.
Yes, but compressing the model is different to extract some layers. So just as do with the tiny YOLO or YOLO Lite. That's a different way. It's different
Yes.
from compressing the model.
Yeah, so I think I think what they do with the tiny YOLO is that they have the same YOLO architecture, but just with a fewer layers, right? That's true. So yes, I mean, that model can still work, but you know, sorry, could you what do you what is the question? I forgot. Like,
Let,
could you repeat it?
let me to think about it. In YOLO, we set the hyperparameters value to obtain the best the best model that we want, that we can. But with the same hyperparameters, you could can we make the same goals, the same ¿cómo se pronuncia? The same behavior. The same behavior.
Oh,
Using these same values, the same number of epochs, the same batch size
with a
on
smaller
the
model.
lighter version of YOLO, just like
Well,
YOLO Lite.
I think you cannot get the exact same, but you get an approximation, right? You will get like something close to it, not exactly like the same one. But even as you notice that the performance a little bit worse, right? Because it's trying to do the same behavior like you mentioned, but it can't because it's not complex enough. It is like how can I say uh Well, the example that I give to my students the other day was that you have this bike, this motorcycle, right? And when you are a very experienced rider, you really pay attention to the torque, and you pay attention to, for example, how does it accelerate? You pay attention to the weight, right? You could, that is if you're a very experienced rider. You could be a less experienced rider, and you and you can not focus on this stuff, but you can still ride the bike, right? It's just that you wouldn't be able to do the same tricks like as an experienced rider, right? Because the experienced rider know, okay, I can push it until here. This is the angle that I can push it, right? But they still both can run on the street. They still both work, but one of them is just marginally better, right? You don't always do the wheelies, or for example, like that, right? It's the difference, right? So in this case, the rider represents the model, and the motorcycle represents the bike, right? Sorry, the data represents the bike, and the model represents the rider, right? So a complex model will pay attention to all of these little things. A simple model will not pay attention to stuff, right? But they will still, right? If that can answer your question.
Thanks a lot, my man.
Yeah, no problem. Thank you. Remember, everybody, if you like what we're doing, please give us a like. Subscribe to this channel. We are trying to make these workshops something big, so we want a lot of people to see it. So please be kind enough to like us.
Yeah, we have another 2 questions from James. The first one is how to select the suitable activate function.
Oh, nice question, James. So the simple answer is that for the hidden layers, you pretty much all the time select ReLU or some variant of ReLU, like CeLU or ELU, but they're like the same. In my opinion, they're like there's not a big difference between each one of them. But for the output one, the output is actually a very important case, because the activation function basically is that the function that determines the range of your values, right? For example, in this case, I'm dealing with the normalized Euclidean distance, right? So what kind of values can my function get between 0? So 0 is the minimum distance, right? And 1 is the total distance of the fingers. So I need my function to bound my values between 0 and 1. Let's take another example. What if I'm trying to predict the position of maybe I want to give a score of whether if this hand is of a hand, if this hand is of a male or a female, and I give it a score. So 0 corresponds to male, 1 corresponds to female, right? That's why I would need like a sigmoid, like the one that I have right now, because there's only two classes, right? Let's take another example. Let's take that I want to predict the house prices, right? A house price is not bound by 0 and 1. It's bound by 0 and infinity, right? So in this case, I will use a ReLU function, right? Let's say that I have a model that wants to looks at the environment and tells my little robot if go left or go right, right? So in that case, I will use a tan H model, because then the tan H would tell, like, let's say -1 is totally to the left and 1 is totally to the right. So that value represents a physical thing, right? That you're trying to predict. That's how I would say that you choose the activation function. But in the hidden layers, I have been studying deep learning for 5 years, and I always use ReLU, and I don't bother to use anything else because it has shown to have some improvement. The improvement is quite small, right? And there are other hyperparameters that affect the network's behavior more than this one, right? But for the output, the output is crucial to choose the correct hyperparameter. Sorry, the correct activation function. Thank you for your question.
The second one from James is How to prevent overfit problems for training the small data set?
Okay. So overfitting happens when your model is very complex. In other words, it has a lot of parameters, and your data is not complex, right? You have either a few data set or you have several stuff of the same thing. So the way to solve it is to reduce the number of parameters, right? Make the model more simple. Because in the end, right, what we want is some model that can generalize to previously unseen data. And if the model is overfitted, then it will be able to perform very well on the training data, but not so good on the testing one. Another way is that, okay, you can keep a rather complex model, but the thing that you can do is apply regularization techniques. Regularization techniques like, for example, L1 regularization, which penalize the absolute value of the weights of the model. L2 regularization, which penalize the summation of the squared values of the weights. You could apply, for example, dropout, which dropout drop certain neurons of the network at random. You could apply batch normalization, which basically subtracts the mean and divide by the standard deviation of the batch. In my case, you saw that I have the batch normalization, right? And I have it at every layer because I want to have a lot of normalization. That also helps for preventing overfitting. So you can try that. In my case, for example, even if my model was too complex, right? That effect will be diminished by the fact that I have a lot of normalization in my model. There is also drop connect that doesn't drop the layers, doesn't drop the connections, but just freezes them. There are many different regularization things. That's also a very interesting part of deep learning, just like model compression. And it's people study PhDs on just this topic, right? Yeah, so thank you for your question. I hope that I answered it. All right. So with these guys, I would like to thank all of you who are watching us live and all of you who are watching us later. We really appreciate all of your support. We still have 2 more workshops, and I think they're definitely good and stuff to look forward to. And we just with this, we'd like to say goodbye to everybody and thank you for joining us.